All right, everybody. Happy Thursday, Thursday, Physics Friday, whatever you want to call it. As of just a couple of minutes ago, I bumped the homework back on the request of someone, so you can thank your fellow student that it'll be on next Thursday instead of next Tuesday. Okay. It also makes sense since we're just now finishing up the material today a little bit. So a week from today at 11:59 p.m., the next homework is due. Okay? And just one assignment that day. That's all you have to worry about for that one day. Not like a billion assignments, just one assignment over capacitors. Okay? So this will encourage you to be working on this material and making sure you understand. So let's see. We finished off last class with this problem. There were some correct answers. There were some people still sort of working on it as we left. So let me run through the solution for this somewhat quickly and make sure that we're all on the same page. I already had it written out, so I'm not going to rewrite it. So we'll just point at things and talk about it a little bit. So first of all, this situation at the top, over on the left side, why is that not working? There we go. We've got these two capacitors which are in series, one right after the other. Over on the right side, we've got these two capacitors which are in series. They both happen to be C1 and C2, which means I really have to do the calculation just once and use it twice. So if capacitors are in series, we use this equation. So we're going to add the reciprocals, and that's going to be equal to the reciprocal of the equivalent. All right. So it was given in the problem that C1 was 5, I guess it's microfarads, and C2 was 10. So if you work this through, add them up, take the reciprocal, you should get 3.33, and that comes out to be in microfarads as well. Once you have that, then we essentially have a capacitor here, that's the combination of these, this one in the middle, and then these two have now been combined. Those three branches of the circuit are in parallel with each other because they all split off from this point and then all come back together at this point. They share the same conductor on one side and they share the same conductor on the other side. So these three branches are in parallel and we can just add those together. So I've got the one on the left, the one in the middle, and the one on the right, and we're just gonna add all those together. So I've got a couple of 3.33s and the one in the middle is 2. Add all that up, you get 8.67 microfarads, and I called that C top, indicating that is the combination of all this stuff at the top, okay? That's your equivalent capacitance so far. At the bottom, we have these two guys, and they are in parallel, so you can just add those together. So we've got C22, which you might call it, or C bottom, it's the bottom part of the circuit. It's just those two added, they're each 10, so you should get, where did it go? There it is. So you should get 20 microfarads for that. Once you get all of that done, then the top part and the bottom part are in series with each other. The bottom follows the top, one right after the other. So those are in series, which means you have to use the reciprocal equation again. So this is what I got for the top part. That's what I got for the bottom part. Take the reciprocals, add them, take the reciprocal again, and you get a total equivalent capacitance of 6.05. Or 6.05 times 10 to the minus 6 if you convert it to farads, okay? So that was the equivalent capacitance. It also asked us to find, what was it? The charge on this middle capacitor, which is hiding in the middle of everything. Yeah. Question.
Is there any particular reason why? Does it not matter if the series look different on that diagram than the one we had on Thursday? So it was like,
What did it look like on Thursday? This?
yeah, is it not? Are they both the same?
They're both the same because C1 and C2, they're both along this branch. Whether I put them right next to each other or put them on this side or here, it follows that you go through C1 and then C2 before you get to anything else. Those are in series. Anyone else? Anything else we want to talk about? Anything bothering you? Switch back. I can switch it back, yeah. Next time, just run up here and just swipe the screen. It'll be fine if I'm not paying attention. Right? So to find the charge on that middle capacitor, we have to kind of work backwards a little bit. So let me see if I can keep some of that up and also show the new work here at the bottom. So remember, we have this rule. If things are in series, if capacitors are in series, they have the same charge. So that means that total combination at the top and the total combination at the bottom, which we said were in series, have to have the same charge, and it's going to be the same charge that leaves the battery. It's like it goes from the battery, hits the first one, and then sends the same amount to the second one, and then you're done. Okay, so whatever the total amount of charge is going to be the charge that you have for the top combination and for the bottom combination. So I started by doing like a total circuit calculation with this equation. The total amount of charge is equal to the equivalent capacitance times the total voltage. So once you have that, you get this number for the total amount of charge. So that's how much goes into the top part, and it's how much goes into the bottom part, those two parts in series with each other, okay? You can also say that anything in parallel has the same voltage. So that means when we go back to this top part, that this left side, the middle side, and the right side all have the same voltage, okay? So we're going to just look at the voltage of the top. The top part all has the same voltage, which will be the same as the voltage across just the middle one because they're all the same. And I already know the charge there, which we just found, and I know the total capacitance of that top part, okay? Dividing those two tells me how much voltage I have for all the things at the top, all of them individually or all of them combined, okay? Which means I can take and use that value for V3 one more time in this equation. Q equals CV, all threes now. I know the capacitance of number 3, I know the voltage of number 3, so I can find the charge across number 3, okay? These problems all basically work the same. Put everything together, find the equivalent capacitance. Once you have that, you can find whatever's missing as far as the total using this equation, okay? So you've got Q equals CV where I have essentially total for all the things, and then I can repeatedly apply that exact same equation for combinations that I put together or for any individual capacitor. You just have to work through trying to figure out what you know and what you don't know using that equation over and over. It gets a little confusing on the second part, especially, I think. Yes, maybe a little bit. That is one of your homework problems that's due next Thursday. So you're welcome. Ta-da! We have one of them done. Of course, you're going to have different numbers, so you'll be forced to sort of work through it a little bit again. Okay? Any questions hiding in there anywhere before we wrap up this chapter and do a little bit of work on the next one? Anybody? Yes.
I guess we might go into this later, but what is the relationship between capacitance and resistance and why they're both flipped for each circuit?
Yeah, let's hold that for now. We're going to talk about resistance in this upcoming chapter, probably today. So maybe your question will get answered, and if it doesn't, ask it again. Okay? All right, so I'm going to jump back a few slides. I put that in the end to this slide on electrical energy storage. Electrical energy storage. And we're not going to do too much with this. We already sort of understand that capacitors are storing charge. If they're storing charge and I can use it to do something, it makes sense that they're storing a type of energy, a type of electrical energy. So I'm just going to give you some equations for this. There's no need to derive them. I just want you to be able to use them. Taking a quick glance at the derivation here. No, we don't need to do that. I will just tell you that the energy that's stored, and yes, this is electrical potential energy stored by a capacitor. is equal to Q squared, the charge on the capacitor, divided by 2C. At least that's one version of the equation. Q squared over 2C. It turns out that because we know that Q is equal to CV, we can get two other forms of the exact same equation. So I can start by plugging this equation in for Q in the numerator, and then we're going to have C squared V squared over 2C. And one of those C's is going to cancel out so that I have CV squared over 2. So notice the first one was in terms of Q and C. The second one is in terms of C and V. You might get the idea that the third version of the equation will be in terms of another combination of those three variables. So we can make one other substitution, and this time I'm going to rearrange this one. We're going to solve this for C equals Q over V. We're going to plug it in for C. And then we get, let's see, Q over V times V squared over 2. So the V cancels, and then I just have QV over 2 as our third form. So three different sets of those three variables. Just depending on what you have, you can find out how much energy is stored in a given capacitor, or in the whole circuit if you find the equivalent capacitance. Okay? And that's really all that I wanted to say about that, which brings us to the last thing in this chapter. This is a relatively fast chapter compared to some of the other ones we've done that we dwelled on for a while and did long, detailed, confusing things. I think this chapter is a little easier than some of the other ones we've done, especially like Gauss's Law chapter. And some of that stuff back there got a little bit rough. There's still some confusing topics in here, but I think overall this is a slightly easier chapter, which is good. And if you like this one, the next one is even easier. So it's like we're going in reverse. It's like we started out hard, and now things are getting easier. Maybe. Maybe not. Maybe it's just what I'm thinking. So, last thing we need to do is this idea of dielectrics. Dielectrics. Remember we said that in a capacitor in between, there's something insulating in there. Everything we talked about so far was just, let's let the insulator be air. Or let's let the insulator be a vacuum, which from the standpoint of a capacitor, they might as well be about the same thing. The difference isn't great. But we can take other insulating materials and put them in between the plates, and it turns out that we can get better capacitors that way, okay? There are a few reasons and explanations here. Let's see. I guess the first 2 points there are reasons why it gives us a better capacitor, and the second two are more about what happens, okay? So I guess it shouldn't all just be in a list of 4 things. 4 things I want to tell you about what happens. So first of all, dielectrics, or an insulating material that is a solid material, or I guess it could be a liquid, but that's not used nearly as much, don't do what we call break down as easily as air can. Dielectrics don't break down as easily as air. What we mean by breakdown is when an insulator allows charge to pass through. Dielectric breaking down is what happens when an insulator, which isn't supposed to let charge pass, does allow charge to pass through. This can happen when V is very large. Think about lightning. Lightning is charge passing from clouds to Earth, or vice versa, depending on whether you want to think about electrons or positive charges, okay? The thing is, it's not supposed to be able to get to the ground. There's all this air in between the clouds and the ground, and there's a very large potential difference, or V, between those points way up in the atmosphere and the ground. So what happens is that if that V gets large enough, if the potential difference is high enough between the clouds and the ground, all of a sudden the air essentially becomes a conductor when it's not supposed to. It's not supposed to let the charge pass through. But because the voltage is so high, the charge is just like, I can't help it anymore. I need to get to the ground. It's like the forces are so strong that they go through the material that it's not supposed to pass through, okay? So this is something that can happen quite a bit, but again, it requires very large voltages. So if I put a dielectric in between the two plates of a capacitor, it means I'm able to turn up the potential difference higher without having to worry about charges feeling so much force that they jump through the air to the other side, okay? Higher V means I'm able to get more charge on the plates. Q is equal to C times V. Make V bigger, you get more Q, okay? So it allows me, first of all, to get a higher voltage, which gives me more capacitance because I'm able to store more charge. But also, I don't want the two conductors of a capacitor to ever touch. But you remember our equation? We said the closer that we can get them together, the stronger the capacitive effect, because it's like they can sense each other. They know to repel the charges off the other plate. And you get more charge storage if you can put them really close. Well, it'd be great if I could like build these things and be like, okay, lower the top plate. Can you get it a little closer? Can you get it a little closer? Oh, they touched. Start over, right? You don't want to deal with any of that. So if you just take a really thin piece of insulator and just slide it in there, then you can just be like, all right, put the two plates together. They're not touching now. You can just smash them together as much as you want to. You don't have to worry about it because you put a solid insulating material in between. Nothing can get across, okay? So it allows me to decrease D, the separation between the plates, which we saw early in the chapter, increases C, all right? So doing these two things, it has multiple effects that allows me to get a better capacitor by simply putting a solid insulating material that we call a dielectric in between the two plates. So, what happens? First of all, the amount of capacitance you get is just increased by a factor that is experimentally determined based on what type of insulator you're using. Meaning we get something like this. If C0 is the capacitance without a dielectric, multiply that by K, the dielectric constant, and you get a new value of capacitance with the dielectric. And this is kind of how the whole thing with dielectrics is going to work. We're going to have this constant. We're just going to throw that constant in there and it just sort of changes everything. Okay? What's really happening in this equation is that we have a different permittivity now. So instead of having E0, the permittivity of free space, which is what we would have if we just had air between the plates, we now have a different permittivity just known as epsilon. Instead of epsilon naught, just epsilon, which is the permittivity of the material itself. And it turns out the relationship here is exactly the same as what you see above. The new permittivity is just the dielectric constant times the permittivity of free space. Easy enough, right? You just multiply things by a constant. Yeah.
Does a conductor have a higher permittivity than
Does a conductor have a higher permittivity than air? Off the top of my head, I think it's going to have a much higher permittivity because it's readily accepting electric fields instead of resisting them. Anyone else on this particular slide? Yes, no, nothing? You ready for the weekend? I'm ready for the weekend. I'm tired. Way too tired. I'm tired of being tired. You know, you get to that point, it's just like, okay, I'm tired. Well, now I'm sick of that. I just don't want to be tired anymore. And yet, there's one more day left this week. By the way, though, I had to count. I think we're on the back side of the semester now. Meaning, if I remember correctly, today is the first lecture of the second half. Like the halfway point was yesterday. I don't know if that does anything for you, or if you're like, only halfway? maybe that's it. Or maybe you're like halfway already. Yeah, it could be either way, depending on glass half full or empty. I just know that once you get to the halfway point, it feels like it kind of accelerates toward the end instead of like, is the semester ever going to get going? And then the next thing you know, it's over, and that's good. So moving on. Moving on over here. Let's see. Hold on a second. I'm trying to decide if we actually want to do this slide. Does it help you? It does not. We're not going to do this slide. There we go. Moving on. This is the one that I want to talk about. Okay? If you're wondering why this works, why do we get more capacitance when we put a dielectric in between the plates, in addition to the fact like, ooh, I can put them closer together and I can turn up the voltage more. Those seem kind of like secondary reasons. Like, what's the real reason that this benefits us? We can see that on this particular slide, starting on the left, which is just our capacitor without anything except for air in between. We saw this like 2 chapters ago where we have an electric field that points from the positive side to the negative side, and it's just this constant electric field that goes straight across. Because we understand if I just drop a positive charge in here anywhere, it's going to run to the right. Okay, so that tells us the direction of the electric field. So, what happens when we go over here and all of a sudden start inserting a dielectric? Now, first of all, keep in mind, this is a very rough diagram to get the idea across. An insulating material isn't made up of little bugs that have a positive and negative side. It doesn't look anything like that, of course. However, for every molecule and every atom inside that material, there are positives and negatives that are in there, okay? And even in an insulator, things have the ability to move around a little bit if so inclined, but I don't have the ability to just take the electrons and they just go wherever you tell them to, okay? So roughly speaking, if the insulator is neutral, but I still have charges there, equal numbers of positives and negatives, if I take that and put it inside an electric field, as much as they can, positives and negatives are going to sort of realign themselves with that electric field. Positive charges very much want to get away from the left plate, and negative charges very much want to get away from the negative plate. So don't get the idea that like all of the positives and negatives are going to like perfectly line up inside the material now. That's not true. It's an exaggeration just for emphasis. But just think about like random positives and negatives. Now all of a sudden, the positives have a bit of a tendency toward the left, so that now it's a little bit more positive on this side than it is on the left side, okay? Not drastically, but a little bit. If that's true, then a little more positive on this side and a little negative on this side means that in the dielectric material itself, I have another electric field that's pointing the other way. So this is electric field in opposite direction in the dielectric. Dielectric. Okay? So the charges inside are going to tend a little bit in one direction, which creates a backwards electric field inside. Yeah.
Aren't you also minimizing essentially the distance between the positive and the negative if you end up polarizing the other?
Minimizing the distance between the positives and negatives?
Right, so like if you say that because the actual dielectric has its slightly negative and slightly positive side, so if you were to look at it, are you then minimizing the distance between the dielectric and the positive plate?
So like this?
Yeah.
Yes and no. Are you saying that maybe like this side is almost like the other plate of a capacitor? Kind of.
Yeah.
I guess you could kind of look at it that way, if it helps. But I can't say for sure that that's. I kind of see what you're saying. Yeah. Yeah, I don't know. I don't have a good answer for that. Yeah. So we've got this electric field that's in the opposite direction. If they're in the opposite direction, they subtract, right? So you can imagine that now the electric field between the plates is reduced. We have whatever was there before minus a little bit that's coming from the dielectric material itself. So the electric field between the plates is reduced, which results in a few different things. First of all, we can say that my new electric field, well, if it's reduced, it's not going to be multiplied by a constant. Instead, it gets divided by that same constant. And we're not going to deal with the calculations of how or why it's like exactly that amount. Not something you need to worry about for this class. Take an electricity and magnetism class, like a junior or senior level version. Yeah, that sounds like a good time, right? And just have a whole class just in that. And you can find out a little bit more about that. Let's see, but we can take this a little bit further. And you might remember that, let's see, V, the potential difference, is equal to E times D between the plates. So that means now let's write this as V naught and D naught. It means like this has now been divided by K, which means the voltage has been reduced by K. So if all of a sudden I've reduced the amount of voltage, this is what allows me to say, turn it back up to where it was before, or maybe go even a little bit higher. So that means that if now the voltage has been reduced by this amount, we can say that C is equal to Q over V. So we're going to plug that into here. So we've got Q over V naught over K. And then let's rewrite that out a little bit. So now I've got K times Q over V naught. And you can see that now the capacitance has increased by that factor K. Instead of just being Q over V, now it's K times Q over V, okay? So here's the way that this sort of breaks down. E goes down, which means that V goes down, which means that the capacitance goes up, okay? And that's using a little bit of our stuff from the previous chapters. E goes down, so the potential difference goes down, and that results in a higher capacitance. And that is the end of this chapter. Yay. Yay, yay, yay. Yay, 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 yay. Yay, yay. A little bit of excitement out there, but very little. So very little. All right, so let's jump over to the next chapter. And I saw that for the 9th edition, I've been numbering these things wrong. Anybody notice that and just didn't tell me? Yeah, okay. Yeah, I was using the 10th edition numbers for the chapters. So technically this was chapter 26. And I got this one right. This one actually, wow. What does that say up there? 25? Wow, that's just wrong altogether. The file name says chapter 27. Why do all these books have to have different chapter numbers? So this is technically chapter 27 in the 9th edition, which should agree with what all of you have. So this chapter becomes even more practical than the last one. The last chapter was sort of half and half. It was like the first half of the chapter was all theoretical. But then the second half became more and more about like, let's take these devices and actually put them into circuits and see how they work. We're going to have even more of that in this chapter, starting with a little bit of a discussion of the battery and how it creates a potential difference for us to use. So you don't need to know a lot of details, just get the rough qualitative feel for how this works. Maybe some of you did like a science experiment, like in elementary school with a battery and you had to make your own battery or something. So maybe some of you have like already been down this road at some point in your life. Maybe not. Either way, I'm going to tell you just enough for what you need to know for this class. The basic concept of a battery is like this. There is some sort of acid and then 2 electrodes that are in that acid, okay? Some sort of acid and 2 electrodes that are in the acid. What's going to happen is the 2 electrodes are made of 2 dissimilar metals, meaning they are different. And depending on what type of battery you're trying to create and how good it works, there's a lot of study that goes into trying to figure out what metals to use for those electrodes, okay? And the process is that one of the electrodes gets dissolved very, very slowly by the acid, And when it does that, it sends positives into the acid solution. So you can imagine that maybe coming from this right electrode are a bunch of little positives that are leaving that electrode. And it starts to become positively charged. Well, if positives are leaving that electrode, that means what's left behind is net negative. That seems reasonable enough. I take positives off of that because of the acid, then all of a sudden I have negatives left behind. Well, if that's becoming more and more positive in solution, it means that negatives would very much like to leave this other electrode and enter the solution because they're attracted to the positive charges. As that happens, this electrode becomes more and more net positively charged. Okay? So a chemical reaction, essentially, together with some repulsion and attraction, results in these two dissimilar metals that we call electrodes, one being negatively charged and one being positively charged. And if that is true, then there is a potential difference between those two pieces of metal. Not really unlike what we had with the capacitor, right? I had two metals, one was positively charged, one was negatively charged. That gives me a potential difference between those two regions, between those two conductors. Now, that's not a very practical way to build a battery. Can you imagine if the battery you had in your phone had to be like a beaker full of some acid, a couple pieces of metal sticking out? That would kind of suck, right? Not terribly mobile at all. Or maybe, I don't know, maybe it's like really thick and there's like a beaker that sort of hangs out the bottom, but you always have to keep the beaker upright. Otherwise the acid spills out and then nothing is safe. So forget like mounting your phone like on your dash. That's not going to work because acid, right? Nothing's good there. So battery technology, battery chemistry, so very much research, so very much active research, because in many ways, it kind of seems like we've hit up against some walls in battery technology. You may notice over the last, 5 or 6 years, has your battery life in your phone gotten really better? Or is it always about a day? You plug it in every night, you get about a day out of it. Now, of course, during that time, processors have gotten faster. They're doing more than they were. So really what's happening is whatever battery gains are being made in the research into batteries, they're sort of just those gains have been taken out by small incremental improvements in the technology that's inside by making processors faster, et cetera, et cetera. But at the same time, processors get more efficient as we make them better. So everything's kind of staying sort of stable between the battery and the guts inside the phone. What we need is a breakthrough. Someone out there right now is in some lab somewhere and they've got the next battery technology, just trying to figure out a way to like all of a sudden get tenfold battery increase over what we have now. And that will change things. That will change things a lot. Or what about when we get 100-fold increase out of a battery? Yeah.
That's the issue with cars, right?
It's a big problem with cars too, yeah. It comes down to, I think it's calculated like in energy density, like in a certain volume of space, how much energy can we pack into that region? And right now we can get so much into the space of a phone, we can get so much into the space of a car, unless you want to make it a lot bigger and a lot heavier. We need breakthroughs. So if you want a job for the next 50 years, go study batteries and alternate portable power technologies. Yeah.
What happens with cell phones that explode?
What happens with cell phones that explode? Hey, look at that, things went away. Oh, there's a number of things that could happen. Keep in mind that, well, hold on, things went away. Let's fix this first. I can't talk, think, and do all this at the same time. Keep in mind, there's kind of a whole lot that's happening there, right? It could be possible if all of a sudden maybe we make a connection, and I'm just sort of making things up as I go along here, educated guesses, right? Like what if something happens in the battery where I get a connection here where I'm not supposed to have one, with being positive and negative? Charges are going to be very happy to flow between those when they're not supposed to, perhaps, which could create quick heating in that region. Next thing you know, that could lead to fire, and worse things. Why would that happen? How many times do you drop your phone in a week? You know, you drop your phone, you pick it up, you're like, oh, it's good, it still works. You don't know what types of little tiny damage might have been done in that process. Drop it a few times, and then that one next drop or that time you lean against it in your bag just wrong, next thing you know, you make a connection where there's not supposed to be one, just mechanically, then there's fire. So, and things get more and more dangerous. The more energy we're packing into a smaller space, the more potential for that energy to in some way be released. And then you could have bigger fires, bigger explosions. You really don't want something like that happening with the battery pack in a car, an electric car, because ouch, there's potentially a lot of energy that's there. But go figure out batteries, please. Please, it's not my job, it's yours. Yeah.
So then would be a question as to whether or not if we should be putting more power into these batteries?
That is a good question. Yeah. If you do that, how do you keep it safe? Got to think about both things at the same time. So improve the battery technology, and simultaneously you got to have people working on the safety side of things.
Would it be easier to make processors more efficient,
Easier,
per se?
you attack it from both ends, you know. So people are working on that, yes, and I'm sure that they're running up against some walls too as things start to get down into like the quantum realm. I think we're down to 7 nanometer size of transistors and stuff, and nanometers is getting really close to like individual atom kind of size. How much smaller can we make things? There's problems with computing in your lifetime without some major breakthroughs. Who's going to solve it? All of you, go get jobs at Google and fix it all, okay? Yeah.
What about using capacitors in the
Capacitors is a thing. I haven't read a lot about that, but I have heard about supercapacitors.
Because I read something in China, they have a bus that's running on capacitors.
A bus that's running on capacitors. There could be something about either reliability or charge cycles, like how many, maybe it can't charge as many times as whatever we have for current batteries. People are definitely barking up that tree as well, though. Yeah. And also, from what we learned about capacitors, you'd have to slow it down somehow. Like capacitors, they discharge, they just go, and they're done. So you'd have to regulate that output to make it usable for some period of time. It's interesting stuff if you're into it. Because yes, it's a mixture of physics, electronics, chemistry, material science, if you're into that. Like everything kind of comes together. One field can't solve it by themselves. So, to get through the test, though, you don't have to worry about any of that. Just kind of understand the basic idea of what's happening, and you're done, all right? What we want to focus on in this chapter is a little bit more about circuits and why they do anything at all. And we're going to try to relate that back to, well, some of the concepts we've had before. So we've got these dudes here in this diagram. Wow, I got to say, you know, that's just sad in every way. I really should have come dressed like that. How long would it have taken you to notice if all of a sudden I'm just standing here and I look just like this guy, you know? Got on my white t-shirt and white shoes, jeans, I guess. I don't really even know what those are, what's happening here, you know? That'd be pretty fantastic. And then, is this guy the exact same guy? Ooh, now we got both of them there. I think their face is a little different, isn't it? The hair's definitely different. Well, I don't know. They both kind of make me sad in a way. They feel like weird, like clones or something that just nobody put any effort into drawing. And who am I to talk? I couldn't draw that. See, this is why all physicists should just do this. When you need a person, you do that and you say person, see? And then you don't have to worry about whether, you know, they look weird or anything. You're just like, it's a person. Done. Draw a box, put a label in it, and then all is good. So anyway, enough with those dudes who make me sad. The question is, why do charges move through a circuit at all? Why do charges go anywhere? Well, remember, it all started with forces, right? Repulsion and attraction. There's forces that make charges want to go places. Then we talked about electric fields, which is sort of a way to describe the forces that were there without specifically saying, like, here's a force. Instead, we say this region of space has an electric field, and positive charges in that electric field will want to go a certain direction. Then we made the connection from electric fields to potential, which in a way was another way to describe the exact same thing, because we said that if you had a high potential compared to a low potential, positive charges would want to go from the high to the low, okay? And we said that essentially the electric field like points in that direction. It's another way of expressing the same thing. So in some cases, like the first 3 chapters, all we did was do the exact same thing just from different directions, different ways of analyzing the same thing. So that's what's happening in a circuit. In a circuit, charges decide they want to go from one place to another because we've given them a place to go and a reason to go there. Okay, that's one way of thinking about it. So the place to go is like giving them a path, giving them a conductor through which they can flow. A reason to go there is because we provide a difference in potential. We could describe that in terms of forces or electric field if we wanted to, but in a circuit, the easiest way to think about it is in terms of a potential difference. So if we were to think about a really simple circuit of, well, let's just think about water. So these 2 poor guys are holding a hose, and apparently it's full of water, okay? And, well, you can imagine if they hold the 2 ends of the hose at exactly the same height, then the 2 ends of the whole hose have the same gravitational potential, which means the water has no reason to go from one place to another. It's just like, there's no up or down. It's just like, I'm just gonna stay right here, okay? But if one of these dudes decides to drop the end of the hose, now this end is at a higher gravitational potential than this end, and the water wants to go from high to low, okay? In gravity, masses want to go from higher potential to lower potential. That's analogous to what the charges are doing. All of those free charges that are in a circuit, if there is a high potential and a low potential, they're going to be like, well, I'm not going to go uphill, I'm going to go downhill, okay? By giving them this potential difference, we give them a reason to go somewhere else, okay? So, let's see, the potential difference, this difference in height, gravitationally, in a circuit is created by our voltage source, by our battery. So if we go back to this, well, we've created a potential difference between one piece of metal and another piece of metal. Charge will flow from one of those to the other as soon as I give them a path. All I need to do is put a conductor in between, which is why this can be so dangerous in a battery if there's a connection where there shouldn't be. Also, if this potential difference gets high enough, like we said, there could be breakdown. There's just air in between here. There's no reason or path for the charge to flow through. But if the potential difference is high enough, it'll say like, I really need to get to lower potential, and it'll jump across. Okay, and that's what we call breakdown. So let's carry on. There's really, I should describe this last little statement here. Sometimes you will hear this term electromotive force, or EMF, which is a little bit weird, and it's a complete and total misnomer. It goes back to the days when people really didn't understand what was happening, and they said, if charges are going from here to here, something must be pushing them. Well, it turns out not really. Nothing's pushing them. It's just like they are here, and they would very much just like to fall, okay? So anytime you see EMF or electromotive force, what it really means is potential difference, okay? Those are essentially synonymous. It's just another older word that sort of stuck around but means the exact same thing, okay? So charges are now moving, which means we can have a term for charges that are flowing through a circuit, and the name for that is electric current. So very vaguely speaking, electric current is just a description of charge flow from any one place to another. From any one place to another. If we wanted to get a little bit more specific, I can give you an equation for that. But, wow, I still have capacitor notes up here. Those aren't going to do anybody any good, are they? No. So the symbol for current, for whatever reason, is I. I don't think that's helping anybody. C was taken. We just used it for capacitance. So Too bad, we have to use something else for current, so we use I for current. And current is an amount of charge divided by an amount of time. So it's like how much charge goes through a region of space or a wire in a given amount of time is the current. So if I were to look at the units of this, we have coulombs in the numerator, we have seconds in the denominator, and that is something new known as the ampere. So our unit of current will be the ampere. Let me see what is on the next slide. Okay, got it. Current. So we're going to start talking about current, which just means charges flowing from one place to another. If it helps you, and this is totally okay, think about the water back in the hose flowing from one place to another. If you imagine that the water is just made up of a bunch of little water molecules, think of those as the charges, right? There's a bunch of free charges that are in a conducting material, and if I give them a reason to flow from one place to another, off go the charges to another location, all right? So we're going to continue that analogy a little bit with this poor guy again, but I think he changed shirts. Didn't he? Yes. I think they both had on white shirts before, but, or is this a third guy?
His hair shorter.
His hair shorter, really?
It's brown in the front.
So it's the brown-haired guy, but yeah, either he got a haircut or it's a different guy. I don't know. So maybe it's not a different shirt. I have no idea. Not to mention he has this weird disconnected hand that multiple of them that float out in front of him. That is just strange in every way. Okay, so a couple of different things. We're going to talk about a basic circuit. Remember, I said you have to give the charges a reason to go. That reason is a potential difference. They're like, lower potential difference. I want to go there, all right? The way to get there, though, is through a continuous conducting path, which we mentioned a little bit in the last chapter. Just the idea of a bunch of wires that are all connected to devices and form a closed loop. They form a loop, and you can just go around and around and around and around the loop forever and ever. You have to have a continuous closed conducting path in order for current to flow. So you can see in the diagram at the top, well, it meets both of those things. First of all, this is my battery. Between one side of the battery and the other, there is a potential difference. So charges have a reason to want to go somewhere. So on the top side of the battery, that is a place of high potential, and the negative side is a place of low potential. Notice they draw that with a gap in between. The way I like to think about this is hiding in between this gap. This is where all the chemical magic is, and I don't think I can make this small enough to actually fit it in here. Chem magic. They move the charges in there in one direction, right? That process we looked at on the first slide, it takes the positive ions from one side and they go over to the other side. That's happening in one direction. So even though this is high potential and this is low, the charges can't go that way. The chemistry inside prevents that from happening. We simply draw that as a gap in the circuit to sort of indicate that they can't go that direction. So instead, they're like, well, the next shortest way for me to get over to that lower potential is to run this way. Whee! And then they're happy because they made it to the place of low potential, right? Now, keep in mind, we're describing all of this as if it is positive charges that are moving. That is only a convention. It's something people decided a long time ago. Whether it's right or wrong doesn't really matter because the math works out the same way. We're going to talk about that a little bit more in this chapter, but not quite yet. So we are imagining that positive charges leave this side of the battery and flow that direction. Now, notice this little apparatus. This is something new. This is a switch. And the picture of it describes exactly what it does. A switch is simply something that will allow you to either create a gap in the circuit. If there's a gap, charges won't flow, or to make a connection so that I have a continuous conducting path. So if you close the switch, that makes a connection here, and now charges can actually go through. As long as that's open, all the charges just sit there. They have no way to get to that lower potential. All of this part here is the same wire, which means it's an equipotential surface. So all the charges just sit there. They're like, this is great, we have nowhere to go. If I make this connection though, they recognize that there is a point of lower potential and they fall to that lower potential, okay? You can see here in the middle, we've got something like a light bulb. It's just a device. The charges are going to flow through there. They will interact with what's there. It turns out it lights the bulb up on their way back around to the battery where the chemical process just sort of keeps going and around and around and around and around we go again. But how does that compare to this thing at the right? Really, this is a water version of the exact same idea, okay? So this water wheel, you might think of it as the light bulb. It's where the electricity, the current flow is actually doing something. On the left, we have it lighting up a light bulb, creating light. Here we have it mechanically turning something. It's doing some work. It's creating something out of the water that's just flowing through it. Let's see, on the left-hand side of this dude and his bucket and his weird disconnected arm is the battery. Okay? Essentially, it's doing work to create a potential difference, which you could think of as here, the person takes water from low potential and lifts it up to a high potential in order for it to be able to go back and fall back to the lower potential, okay? The battery does work in the form of a chemical reaction. Here, the person is doing mechanical work, lifting the water up to another height, okay? And then you can, of course, see that, like, as long as I give it a path to flow down, well, the water is going to want to go back down here to the place that has low potential, okay? And then it's all just kind of hanging out down here until this guy picks it back up, and then it wants to flow around this way. And you'll notice this is a closed path, a closed loop that the water can flow around. Now, don't make the mistake in thinking that, I don't know, like it says here at the bottom, charge is not produced by the battery. So it's not like, I don't know, like the battery dude here on the left is like a massive bucket of charge, and he just takes the charge and like slowly pours it into the circuit. And then eventually when he runs out of charge, like that's it, battery done, need a new battery, okay? That's not what's happening. The thing that the battery is doing is creating a potential difference. It's not creating charge. It's simply taking the charges that are there and it's doing work on them, okay? So you'll notice in this water circuit, there's water everywhere, right? There's water here, there's water here, there's water here, there's water here. There's water everywhere around that circuit. Over on the left, think about what's happening in all of those wires. Are they empty? No, they're not empty, right? There's 3 electrons that are everywhere. There's charges everywhere in all of this conducting material. It's just that when I give them a reason to move in the form of a potential difference, it's sort of like all of those charges then go and they rotate around the circuit, okay? So it's not like charge is being produced and then just dumped into the circuit. It's more like something is taking what's already there and making it move around in a loop. Do you see the difference between those two? Are we okay with that concept, that idea? Is anybody out there? Yes. Okay, good. Let's see. I think that's about all I wanted to say about that particular diagram. So, let me point out once again that we have this assumption that it's positive charges. Everything that we talk about in this class, all the way back to electric field, we said it's the direction that a positive charge would go. This is because back in history, we didn't know about electrons. We knew that some of this stuff was happening, but people were like, I don't know. Maybe it's the positive things are moving. And then later on we discovered, oh, it's not the protons that are moving, it's the electrons. Let's just keep saying what we've been saying all along, which is a little bit frustrating because it's not actually what's happening, okay? So we are making an assumption of positive charge flow. This is specifically known as conventional current flow. It is the convention that everyone, at least in the physics world, uses. There are other categories of people out there, maybe engineers, I don't know, maybe engineers, maybe other people that decide to say like, hey, it's actually electrons moving. Let's do everything in terms of that. But in the physics world, in all the physics textbooks, we stick to this old school way of doing things, which I don't know that I terribly agree with, but we have to all be on the same page. We're pretending that it's positives moving. So in other words, when I look at the circuit, we are going to say that the current goes around this way, as you can see as described, because we're pretending that the current is made up of a bunch of little positive charges that are going that way. That's the way we'll work all the problems, even though what's technically happening is that electrons are leaving that side and they're going around this direction. It's just the difference between a positive and a negative. One case we're saying it's counterclockwise, one way we're saying it's clockwise. It's the same amount of charge, either way that you look at it. Mathematically, it works out the same, okay? I just want to point out that that's actually what's happening, even though we don't discuss it that way very much, okay? Now, in the circuit, like we said, there are these electrons everywhere. These are conductors. They're full of electrons that are just ready to move if I give them a reason to move. So, when I make a connection to something like a battery and give it a complete path, like we said, all of those free electrons start moving all at once. It's not like one leaves the battery and it's like you got to wait a little bit for the light bulb to light up because it's like, well, I got to wait for that electron to get over there. Well, that would be frustrating, right? It's like you come in and flip the light switch and you're like, and the electron has to like travel this distance to get there. No, you flip the light switch on and immediately all the charges begin to move, which means the charges that were right next to the light bulb immediately start passing through there and you get an almost instantaneous effect. All the charge that's everywhere in the circuit begins moving immediately. Which brings me to this little thing here at the bottom. The electrons aren't quite like water. When we talk about water flowing through and we use that example, we just imagine like, oh, it's just like a steady stream of water that just begins moving. Well, it's not like in a conducting wire that it's just empty on the inside except for just like this fluid of electrons just waiting to like flow. Instead, of course, inside here, there's atoms, like nuclei of atoms that are sort of sitting everywhere. And it's a solid material. All this stuff is bonded together. So when the electrons decide to start moving, well, they're not free to just like go. They're going to run into stuff along the way. I think that sort of makes sense, right? It's almost like they have to run an obstacle course to get anywhere. So they're kind of like, they're just sitting there, right? You make a connection, you flip the switch, there's a battery, there's a power source, and they're all of a sudden like, yay, let's go! And they're like, boom, and they run into something, right? And they're like, but I still want to go. So they're, and then they go, they find their way around that, and then they hit something else, and they're like, oh, and then they run over here and they hit that, and then they go, that you can tell, like they're getting there slowly but surely, but they're running into all of those atoms along the way, which means they end up taking a path that maybe kind of looks like that, okay? It's kind of crazy. They can't just go down the wire. They end up taking this sort of meandering path because they're colliding with things along the way that make up the structure of the conductor. That causes some problems, right? You can imagine that every time they hit something and go off some other direction, that's a collision. That's a literal physical colliding of things that releases some energy and actually loses some energy in a way, okay? That, all of these collisions, is what we refer to as resistance. The fact that the electrons aren't just free to go, that there's a bunch of stuff in the way, gives rise to resistance. it opposes the flow of the charges. It makes it more difficult for them to move. Does anybody want me to bounce around the room a little bit more until I fall down and hurt myself and then class is over? Yeah, I thought so. I should just start running this way and just see what happens. All of you are going to be like, please don't touch me. Like, what if I just tried to run across the tabletops? How far do you think I make it before I break my leg? Sounds like fun, right? I can tell you right now, I'm not that athletic. I'm a physicist. What do you expect? Not that limber, not that coordinated. So I might make it to the first desk. Should we try it?
Let's hold it down for you.
You'll hold the desk down for me? Okay.
Do a step on it, you just go to face.
It's not going to be good, no. So if y'all could all stay seated very firmly, and then I'm going to try to just run across the tabletops. Part of me wants to just try,
I know.
but at the same time, I really wish that the floor was just covered in like airbags, right? So that I could try it and not actually hurt myself.
I don't think you could do it.
Oh, here we go. I hear the reverse psychology happening out there. I already told you I can't do it. I'm aware. You should go the other way. Like, I think you can do it.
Yeah,
Oh,
let's go.
all right. What's your question?
Does that mean that the smaller the wire, the less resistance?
Smaller the wire, the less resistance. It actually works out the other way. The reason being the boundaries of the sides of the wire. So if I reduce the area of this, there's less ability sort of for the electrons to have more sideways motion to sort of make their way forward, and instead it may immediately hit a wall if I restrict this too much. So it's almost like the walls and those boundaries all of a sudden magnifies the amount of difficulty it is, because now there's just even a smaller path for them to try to cram their way through.
So it's like
A highway with
obstacles.
a highway with obstacles. Yeah. Yeah, you could think of it that way. So it's like the difference, if you're taking the same amount of cars and trying to put it through a 4-lane versus a 2-lane highway, all of a sudden there's just more restrictions from the sides and everything doesn't flow as well. On the way home today, you should all look at traffic and imagine electron flow and think about what's happening. And then don't do like this on the road. This is no way to go down the highway, okay? Please don't. Otherwise, you're going to get pulled over and they'll be like, Dr. Lohorn said this is the way to drive. You're like, no, I didn't. I have a recording. I never said that. I didn't say for them to drive that way. So there we go. Let's see. Is there anything that I wanted to add to this particular slide? Let me just double check. There is not, okay? At the end of this chapter, we're actually going to calculate how fast the electrons are moving. You'll be surprised, they don't move very fast. It's really quite depressing. I want to do one more thing, and then I'm going to let you go for the week, and that is a connection between resistance and current and potential, known as Ohm's law, which I'm sure many of you, if not all of you, have seen before. V equals IR. Although maybe you can see this in a slightly new light now. So we know what all of these things are. This is potential difference. This is the current. And this is our new thing known as resistance. So it makes sense that if I provide a potential difference, I connect a battery, right? It's like there's this much potential difference. There's this much reason for the charges to flow. Well, now the current and the resistance are inversely proportional. If I can lower the resistance, I'm going to get more current. And if I increase the resistance, I'm going to get less current. And that's all just based on how much difficulty or objection you might think that the wire does to oppose the current flowing through. One thing I should say, though, is that even though this is called Ohm's law, it's not really a law. It's not like everything has to obey it, okay? Instead, it's more of a description of how some things work, okay? So we actually have materials, and we say that they are ohmic in that if I apply a certain potential difference and look at how the current and the resistance change, it's linear, it follows the equation. Other materials don't necessarily work that way, and we call those non-ohmic materials. So this is only a law that applies to the things that obey it. What kind of dumb law is that, right? Also, don't use that with cops either, right? It's like, this law doesn't apply to me because I don't obey it. I don't know. So Ohm's law, this should really be called like Ohm's relationship or something, because law is just not the right term for that, all right? Let's see. The rest of this, let's get into next week. What do you say? Okay? So take Ohm's law home with you and think about it or something. And don't forget, homework due 1 week from today. Goodbye. Have a good rest of the week. Good weekend. Miss me or something. I don't know. You can at least say bye. Bye. Bye.
I think